All right. All right. So welcome to this episode of the Spartan series. My name is Jim Ostrowski. I'm talking today about camera calibration. It's basically how do we use information coming from a camera to understand information from the world, and in particular, it's knowing about how that camera works that is going to be important in camera calibration. That's what I'm going to focus on today. Maybe before I get started, just a little bit about me. My background is in robotics. I've been working in robotics my whole life, my whole career. I started with a PhD in mechanical engineering at Caltech, and then went and was a professor for a number of years at University of Pennsylvania. Worked in the GRASP lab, the robotics lab there, before leaving to join a startup company in Los Angeles called Evolution Robotics, where I worked on all sorts of computer vision for consumer robots, toys and vacuum cleaners and things like that. And then most recently I've been in the Bay Area working at a company called Blue River Technology, where we're doing smart agricultural systems, but again, using cameras to try and figure out what's going on with crops and weeds on the ground and treat every plant individually. So it's an exciting company to be working for, and we were acquired a couple of years ago by John Deere, which is a big agricultural equipment manufacturer. So it's also been just really fun. And I'm now a mentor for 971, and for better or worse, this is my first year. So it's a very unusual year to get started, but one of the things I've been working on is this camera calibration. So just jumping into it, things I want to talk about are really pretty simple. What is camera calibration? So just kind of try and give an overview of what I'm talking about and why it's important. And along with doing that, just give you a sense of kind of a model of how a camera works. And so when we talk about intrinsic camera calibration, I'll define that. It's kind of how do the internal parts of the camera and its lens work. And then I'll spend the second half really of the talk talking about how 971 has been approaching intrinsic camera calibration and some of the tools we've been using. And then talk a little bit about just ways this gets used and important things to think about. So maybe just to start, what is camera calibration? And really camera calibration takes two parts. And it's thinking about kind of the internals of the camera. And again, I mentioned the lens, but also the sensor itself, the imaging sensor, and how they're mounted relative to each other. And that's called intrinsic calibration. And that's what I'm going to focus on today. And then there's a whole nother area, which is extrinsic calibration, which is really understanding where the camera is relative to everything else. So it's understanding where is this camera mounted with respect to, say, a robot frame or some world reference frame. But kind of where is this camera relative, and maybe also relative to other cameras. And that's called extrinsic calibration. I'm not going to talk about that today, except for a couple references. But it's also very interesting, and it's something that we're just getting started doing. Hopefully that's a Spartan series talk for next year, and it'd be fun to do. So just when I think about, and maybe just one last mention of extrinsic calibration. Extrinsic calibration is kind of showing you where the camera is. And I'll talk about reference frames, like this is a coordinate frame. And in 3D, the extrinsic calibration will be kind of a map between those two frames. And I'll talk a little bit more about that. Also, just want to reference that the online documentation in OpenCV, the Open Computer Vision libraries, are really good, and I highly recommend it. I've put a few links to some of the documentation throughout this presentation. So I definitely recommend taking a look at those if you have any questions. So let's start with why is camera calibration important? It really impacts very directly how good and how accurate your estimates are of the world. And when you're using cameras, you're generally trying to figure out where things are in the world, where you are in the world. And so if you want to have good estimates of that, then you need to do calibration. And I'll talk about a little bit about how you do it. If you can't do sophisticated calibration, how you could do some just basic calibration. For intrinsic calibration, this is driven a lot of times just by cheap lenses and cheap cameras that introduce different types of distortions, and I'll talk about those. And in particular, if I don't have a good intrinsic calibration, then I can introduce errors in heading in the direction to where things are, and that introduces error. That error propagates into my estimates of where things are in the world. Also, intrinsic calibration is really important if you're ever using stereo cameras and trying to estimate the depth of something, because those intrinsic parameters, the intrinsic distortions will warp where you think things are, and so it warps your estimate of where things are in terms of their depth in the world. For extrinsic calibration, it's the same basic idea. Is if I don't know with high precision where my camera is relative to, say, my robot or to other cameras, then my estimate of where things are, the estimate that I get from the camera of where things are, it's only as good as the estimate of where that camera is to the robot. So all the errors that I get from where the camera is relative to the robot propagate through to those estimates of where things are in the world. Also, when I start thinking about extrinsic calibration, if I have multiple cameras, it becomes really important to know where they are relative to each other, so I can kind of put information that I have from one camera and map it into the other camera's frame. And this is, again, really important for stereo cameras, but also if I think about multiple views from a robot that I want to fuse the data from, if I know where those cameras are relative to each other, that makes it that much more accurate. And as I kind of alluded to, if we can't calibrate or don't want to, there are some basic things we can do, and I call it kind of CAD values. So for extrinsic, I know where in CAD I design the camera to be relative to my robot frame, and so I can use those values. It can be really hard to get good accurate values, especially around angles, because tilt is really hard to measure. Even a couple degrees can make a big difference. So getting those values can be tough. The intrinsic calibration parameters, you can't really use tape measure to measure them, but I'll give some tips on how you can estimate those in just a minute. Okay, so maybe I'll spend just one more minute on extrinsic calibration before leaving the topic. Extrinsic calibration is, again, about where's the camera relative to some coordinate frame. So here I've picked this coordinate frame O, and that, say, is my robot reference frame, and I'm trying to figure out where that object is relative to the robot. This could be a point on the field, it could be a ball that I'm trying to pick up. And so what I really need to know is how to get the robot to that object. But what I'm measuring is where is that object from the camera frame. So what I'm getting is information about the object in this camera frame. And the extrinsic calibration is about the map that can take me back to the robot frame. So it's that map, I call it R and T for rotation and translation. And knowing that allows me to take a point that is measured in the camera frame and map it into the robot frame. So again, if I see it in the camera, I know where it is. Now I can figure out where it is relative to the robot and go pick something up or drive to it to drop something off, or shoot a ball into a target, as might happen this year. Okay, so now let me jump more into intrinsic calibration, again, the internals of the model, of the camera. And so to do that, I need to really talk about what the model that we're going to use for the camera is. And intrinsic is basically figuring out the parameters in this model. And for this, we use what's typically called a pinhole model or perspective projection model. And I'll walk you through what that means. But effectively, it's saying that if there's some point here, again, think of this, maybe this is the location of a ball that is out here in space, and I give it some coordinates X, Y, and Z relative to my camera frame. And the camera frames are interesting. Just by convention, we typically say that the Z coordinate of the camera is kind of pointing out of the camera. This would be kind of along the focal axis, or where the lens pointing. X is to the right and Y is pointing down. So those are the typical coordinates for a camera frame. But if I've got some point measured in the camera frame, the idea of perspective projection model is I project down to an image plane. So this is kind of a plane that I'm projecting through. And the way I project down is I draw the ray between the point in the world that I'm trying to measure and some focal point. And this is kind of the pinhole point. There's a point that represents where the camera is. And I take that ray and I intersect it with the image plane. And wherever that point is that it intersects is where that part of the world that I'm viewing will show up in my image. So it's a projection from the real world that has a 3-dimensional space down to a planar image, which is 2-dimensional, that's just along that ray. And so when I do that, there's a bunch of things that come along that I need to know. First off, I said I take my point X, Y, Z in 3 space and map it down to the coordinates I'll use here are U and V, where U is kind of horizontally along the camera X-axis, and V is vertically the camera Y-axis. And think of this as just kind of a pixel in my image. So if I got a 2-dimensional image, U and V is just telling me where in the image this thing's going to map to. Other things of interest or important to note is what's called the principal point, and that's the center of the camera, center of the image in effect. We call that CXCY as the camera center. And there's kind of in the X and Y direction. So this is just where the focal axis of the camera intersects the image plane in the image coordinates. So this is kind of saying, where is the center of that camera? And then last thing that I'll reference and use is the focal length. And that's the distance from this point in which all these points that I use as my projection point, my focal point, if you will, and the distance from that point to the image plane itself. And so if I think about that being measured along the focal axis, that's this along the ZC axis, it's just the distance along there, and we'll call it F. So the Z coordinate of the image plane is a distance F away. Okay, so those are all the basics of the camera, and I'm gonna add a few more details to it in just a second, but that's basically how this perspective projection model works. And like I said, we're gonna have a bunch of parameters that get introduced here that we have to estimate to do calibration. Because at the end of the day, what calibration is gonna do for us, intrinsic calibration, is gonna make sure we're getting the right model of how something in the real world projects down into our image. Okay, so to do this, the first thing we wanna do is figure out, and I'm gonna jump back and forth a little bit here, is figure out how to compute U and V given X, Y, and Z. So if you tell me where X, Y, and Z is for this point in the real world, what's my U and V? And the way I want to think about this is similar triangles. And I'm gonna simplify it a little bit by just looking in one planar section, cross section of this, the kind of Y-axis. But the same thing happens in the X-axis. So if I think about this triangle here, which goes from C to Y and Z, that's the same triangle basically as going from C here to Y up here. And I know I've used capital Y and small y, I apologize. And then a depth Z, so it's a distance Z. So think about that triangle as being something like this triangle here. But I'm just kind of projecting down to this vertical plane, if you will. And again, you would do the same thing for X, but I just want to focus to simplify life a little bit on the Y-axis. So how do I compute V, which is my vertical height of the image point on the image plane? So this is my image plane. We said it's a distance F, the focal length from the center of the camera. And there's a plane here that I'm projecting through. So my ray goes from Y into C, and the image point is going to be at some height V above the center. And the nice part here is if I just look at similar triangles, the math works out really simple. So I've got congruent triangles, right? They share this common angle. And so the ratio between Y and Z of that larger triangle is the same as the ratio between V and F, the smaller triangle. And so Y over Z is equal to V over F. Or if I want to compute the coordinate of the image point, this coordinate V, it's just bring the F onto the other side. So it's V is equal to F times Y over Z. Okay, so that tells me how, if I'm given Y, the point in the world where this thing is, in camera coordinates, I can figure out what V is by knowing F and Z. And the same thing happens in the X direction. Again, let me just bring it up here in this side-to-side direction. If I think about similar triangles the same way, I get that my image coordinate for U is equal to F times X over Z. Okay, so that's the most basic part of this that is going to be fundamental to understanding the rest of it is this projection of image coordinates that basically is just saying divide the say height above the ground or above the camera center by the depth of the point. And same thing here, divide the displacement left or right of the camera center by the depth to get these coordinates. Okay, so that's the starting point. There are two things that we have to add to that. So two adjustments to that basic kind of similar triangle equation that we computed there to begin with. One is that by convention, we don't pick the center of an image to be 0, 0 at the center. We pick it to be 0, 0 in the top left corner. So if I think about an image, think about my camera image, the origin for the camera image is the top left corner. So I start 0, 0 there, and if I go positive in the X direction or the U direction, that takes me to the right in my image. And if I go positive in the Y direction or V coordinate, that takes me down in the image. So when I think of the image as kind of a matrix of pixels or a matrix of values, that's how I'm going to be referencing it. Top left is going to be my origin. That means I have to figure out where the center of the camera, this principal point, center of the image, is relative to the top left corner. So there are these coordinates CX and CY, which are measured from the top left. It's CX over, and CY down is the center of the image, or the center of the projection plane. And what we'll see in a minute, and this is part of intrinsic calibration, is that's not always the same as the center of the image, because the lens and the imager might be shifted off slightly. But so the place where the focal axis goes through the center of the image plane is what we're looking for, is CX and CY. And then the second twist that we're going to add here is that typically focal length is not, in computer vision, is not measured in say meters or millimeters, but it's measured in pixels. And that's a little bit subtle. One way to think about it is here, if I want to think about V, this is just a dimensionality analysis, but V is measured in pixels. Y and Z are metric, so let's say they're in meters. So F needs to be pixels to make the dimensions work out. So F needs to be measured in pixels. But typically we'll have, like a camera lens is typically measured in millimeters, for example. So you hear of like a 75 millimeter lens or 200 millimeter lens or 8 millimeter lens. These are measurements of the focal length in a metric version, but we need to convert them into pixels. And so anyway, I'll talk about focal length more in pixels. The other complicating factor that gets introduced here is that when I start talking about focal lengths in pixels, a pixel may have a different actual length in meters or micrometers in the X direction versus the Y direction. They're not necessarily square. So very often, especially in older cameras, the pixels are all rectangular. So that just means that if we're measuring things in pixels, we may have a different focal length in the X direction than the Y direction. So we end up with two different focal lengths, one in X and one in Y. Okay, so now if I put all that together, what I end up with are the projective equations for a camera. Basically that the offset in the horizontal direction is equal to the X focal length times the X coordinate divided by the depth, plus the camera, the principal point, so the CX. And same thing for the Y direction, the vertical direction. So V is equal to Fy times Y over Z plus CY. And so all of intrinsic calibration is about determining these parameters, these values, so that when we project something into the image plane and want to know kind of where it came from, we've got the right corrective factors, that we're measuring things correctly. And that's really important anytime you want to figure out where something is in the world. And that's almost all of it. The one other thing that comes into play when you're working with cameras, and especially cheap lenses, is that they tend to introduce distortions. So cheap lenses, especially wide angle lenses, typically will have what's called a barrel distortion, or it's also formerly known as a positive radial distortion. But it takes something that looks very rectangular like this, where there's no distortion, and distorts it, making it almost look the shape of a barrel, was where the name comes from. So this type of distortion, again, is typically for wide angle lenses, and you'll see it very, very often when you're dealing with lenses. The kind of opposite of this would be negative radial distortion, which is often referred to as pincushion distortion. It's kind of like you pushed a pin in the middle of a cushion or a sheet to distort it like this. And that's typically more for zoom lenses. When you're at the long end of a zoom lens, you get this type of distortion. And just some example images. You can see this is kind of, it has that feel that you might be familiar with if I'm really kind of have a macro lens that's very close and kind of taking a wide angle picture, or if I'm zoomed in, this type of distortion. And I'm not going to spend a lot of time on this. I just wanted to introduce the concept. The equations are a little more complex. The idea is that we take our kind of projection, the x coordinate divided by z, and we scale it by some factors. And these factors have a bunch of parameters associated with them, the K1, K2, K3 through K6, and P1 and P2. And for the radial distortions, this is where the R squared is basically how far from the center point in the camera the point is. So the further I get away from the center, the more contribution I have, and it's squared or quartic, in this case the fourth power or the sixth power. And I get coefficients that describe how strong of a distortion effect that is. And then also K1, if it's a positive radial distortion, then that'll be positive. If it's negative radial distortion, that'll be negative. That's where those names come from. And then there's a couple other parameters around shear. Again, I'm not going to spend a lot of time on this. This is really valuable and important, especially for stereo, to undistort things properly. Because especially with cheap lenses or very macro lenses, you get a lot of distortion around the edges that becomes really critical to get corrected. And again, there's a reference to more information on that. As part of the calibration, we will get these parameters basically out of the calibration as we walk through it. And just as a side note, we typically are ignoring the ones in the denominator, the K4, K5, K6. So just to let you know that that's how we typically would get it. Okay, so now let's shift gears a little bit and figure out how do we estimate the intrinsic parameters of a camera. So to start, let's just talk about, if I didn't have any fancy way to do it, how might I just figure out what these intrinsic parameters are? What's the ideal case? So let me just walk through that. The ideal case for lens distortion is pretty simple. All those parameters that I just showed you, the K1s and the Ps would all be 0. All right, I would just get a 1 here times x1, and I'd get all the equations would drop out just the same. So if I want to ignore distortion parameters, or I've got a really good lens that has low distortion, I could just set these all to 0 and move on. They are, in my experience, never 0, but with a pretty good lens, they're not bad. Okay, so the second piece is the principal point. So where is the camera center? So in an ideal camera, the imager is situated so that it goes straight through the center of the lens. And so the center of the image is right where the center of is centered on the lens, and so it's right in the middle of the image. So if I want to figure out Cx and Cy, where the center is, it's just half of the width of the image and half of the height of the image. It's just the center of the image. So there's no, nothing fancy they have to do there. Again, the idea of the camera calibration is what happens more often is the imager itself, the sensor that's collecting the data, will be shifted in one way or another from the actual center of the lens. And so you get warping that happens there, and you have to offset for that. Okay, so anyway, the simple way to compute for the ideal case is just put the principal point in the center of the camera. And then the last one's a little bit more complicated, but I'll walk through it real quick, is to figure out focal lengths. So focal lengths, and I realize I only did one of these. There are 2 ways to get a focal length. One is if you know the pixel size in, say, meters, and you know the focal length in meters, then I can basically multiply or divide the focal length in meters divided by the pixel length, and that converts to the focal length in pixels. And I'll have a different pixel size, width and height, depending on my sensor. But so it might be something like, as an example, it might be that I have a 8mm lens, and my pixels are are like 3 micron wide. So I would divide the 8 millimeter by the 3 and get something around 2 2/3 times, I think, 1,000. So it'd be like 2,300 for pixels as my measurement for the focal length. The other way to do it, though, and very often we're given a field of view for the lens. So the lens is, we have a horizontal and vertical field of view for the lens itself. And we can use that, that's just an angle that tells me how big the angle is of the camera. And I can use that in the ideal sense, and again, go back to this similar triangle to compute the focal length in each direction. So the way I do that is, if the field of view for the camera is FOV, say vertical, FOV vert, then this angle right here that I've drawn is 1/2 of that, right? The total field of view would go twice that, but this angle right here is just 1/2 FOV vert. And I know that that angle is kind of the interior angle here for a triangle that has a height that is this height divided by 2. Sorry, this should be W. So it should be I'm sorry, no, it's H. H over 2. So it's the total height would be twice this, just like the total field of view would be twice this, but the total height would be twice this. So if I take H over 2 as this height, and the focal length that I'm looking for is Fy in this case. So if I come over here, I've written it out. Fy is just H over 2, so 1/2 H, divided by the tangent of field of view vertical, right? And I've kind of done the math already, but basically the tangent of this angle is equal to H over 2 divided by Fy. And so I can use that to back out what Fy is. Okay, so this is all the ideal case. If you wanted to just figure out what your camera parameters are supposed to be, this would be the way to do it. And it's a really nice, quick way of getting to the focal lengths. Okay, how do we estimate intrinsic parameters? So this is the approach we've taken for 971 to estimate intrinsic parameters of our cameras. And we've got pretty good lenses. We spend a lot of time trying to get lenses that both brought in a lot of light, had a good aperture, had a good depth of field, as well as had low distortion. But it's still, I think, going to be useful for us to calibrate our cameras using a more detailed method than just using the ideal case. Traditionally, with camera calibration, there have been lots of different ways of doing it. People have used circle targets, checkerboard targets. The targets we use that I really like are known as Chirurco targets. I'll explain them more. But they look kind of like this. They look kind of like a hybrid of a checkerboard target with some more information. And we buy our targets from calib.io. It's just an online company based in Europe. I think it's in England, that sells these targets. We buy them because they're high quality, printed. They also are laminated on an aluminum backing that makes them very stiff. And so they're just really good targets to use. And you really only need one to do the calibration. So, okay, so Chirurco targets, where does Chirurco come from? It's a mashup or portmanteau of checkerboard. So it's got kind of the checkerboard pattern, if you will, and Aruco. And Aruco are these little targets in here. I'll show you a detailed version in a second. They're kind of like QR codes, but the idea is that they're binary coded so that each one can be unique. And the nice part is then I can localize each one very well. The checkerboard is really valuable because it gives me good corner accuracy. If I'm trying to pinpoint where a target is, I really want to be able to localize it very well. So if I had something that's just kind of a blob, that doesn't help too much. But if I have a nice corner, I can figure out exactly where that point is in the image. And I can even sometimes do it with sub-pixel accuracy. I can estimate within, even better than 1 pixel. And having this known target means that I can figure out where everything is in space, and then know where they are relative to each other. And I'm going to be able to back out all the parameters just by kind of doing a least square fit. And there's code in OpenCV that does this for us, but I'll be able to back out all the parameters in my camera calibration. We also, by knowing this, will be able to know where the target is relative to the camera, or vice versa, where the camera is relative to the target. That's always nice. And I do want to mention, even though we purchased our target commercially, and it costs a couple €100, I think, you can always print these out yourself, and you can print them in different sizes and different patterns if you want. That's all available through the OpenCV code. I mentioned scale, and I do want to just emphasize why scale is really important, and because sometimes this gets lost, but the scale is something that you actually lose when you're doing this perspective projection. And so you can think about this, if I take and I'm looking at something, I can't tell the difference between seeing that, say, checkerboard object at one distance, and if I saw that same checkerboard object that was twice its size at, say, twice as far, right? That perspective projection, because we're dividing by the depth, I lose a scale factor out of that. And so, and this is something that probably we're all familiar with, but a big object far away looks the same as something smaller close up. You know, a model car very close up looks like a big car far away. In fact, it's impossible to tell the difference with just a single view of that, if they're truly scaled up. So scale is going to be important, and I think that's why I like these Chirurco boards. And the nice part too is that OpenCV provides a lot of this functionality around detection of the Chirurco boards and driving calibration. So the steps that we use really leverage those tools, and so you know, you've got the same advantage and same tool set that we have from this perspective. To do this, basically we use the Chirurco detection or Ruco detection to do the feature board detection and figure out where the corners are. We then match up the 2D points in our image with where we know those 3D points are on the checkerboard, because we know that we've printed the checkerboard, we know how big it is. We then use that to estimate the intrinsic calibration parameters, again, using some OpenCV functionality. And then lastly, that I won't get into too much here, but we can use that to actually estimate where the camera is relative to the board, and then potentially use that to estimate where other things are relative to the camera. So just let me walk through those steps. Again, I just want to kind of take them step by step and tell you a little bit about how this works. So the feature detection, we've got our Chirurco board, and whoops. Oh yeah, sorry. And just to give you a little bit of detail, this is the Chirurco board. This is if I zoom in a little bit, and then if I zoom even further, this thing on the right is an Ruco pattern. It's a 5x5. You can see there's like five by 5 little blocks of black and white cells. So it's just a binary encoded pattern with each one on the target being unique. And when I go to do corner localization and Ruco detection, the nice part is I can throw this in, and OpenCV has some routines that automatically will go and extract corners. And it's a little bit hard to see here, but it actually shows an ID for each of these corners. So each one is uniquely encoded and has an ID, so I can tell where I am exactly. This is really nice because relative to previous methods that were used to calibrate cameras, where I had to know exactly where every point was and get it just right. Here I can have a subset of points, and I know where they are relative to each other because each one's uniquely coded and each one has its own ID. So I get a great set of information about where a bunch of points are in my image, and then I know from the board where they are in space. Okay, and this is the detect markers functionality in OpenCV. And then we're going to use that along with, again, the knowledge of the board and its dimensions to calibrate the camera. And there's a functionality there. To do this, we need a bunch of sample points. We typically will take a bunch of different views. What I've seen, my experience with this and talking with others, is it's really valuable to have views from different orientations. So have the target frame, the plane oriented differently to the camera. So it's not always just a frontal planar viewpoint of it, but it's oriented with lots of different rotations, out of plane rotations. And it covers as much of the image as possible. So you're trying to figure out how this lens is distorted and how it's shifted at all different parts in the image, so you want to get good coverage of the points, especially around the edge. So we'll take generally over 30, sometimes even over 50 sample images, and then do the same thing where we extract the points and then we throw it into the calibrate camera functionality to estimate our parameters. The other part that's useful here is undistorting the images. So again, I mentioned that distortion effect that happens with lenses. This allows us to compute those parameters, the K1 through K3 and P1 and P2 that I mentioned earlier, and be able to undistort an image. So if I have the slightly distorted image, I can correct it. It's a little bit hard to see there. Whoops. But you can see how kind of the whole image shifts when I go from the original image, which has the distortion still in it, to an undistorted image. And I've zoomed in just to amplify that effect. So you can see here's the red line is just a straight line going across the image. So I've just drawn a straight line that approximates what that edge should be, and it should be a straight edge. But you can see it's kind of curved. It's bowed up in the middle and goes down on the edges. And by undistorting it, I can get something that's much straighter, much more like a straight line. That is the undistorted version of that, the corrected version for the camera distortion parameters. And so just tying this all together, the output from this whole routine is the calibration parameters. And just so you know, if you ever use this and you come to it and doesn't seem just like you're throwing a bunch of random numbers, the output is generally done as a camera parameter matrix, intrinsic parameter matrix, that has fx and fy along the diagonal and cx and cy in the right column. And so you get values for those that you can then use to correct your estimates of things that are seen in the camera. And just as a comparison, I'll note, if I went through all the ideal calculations, my focal length in the X and Y would have been around 457. So compare that with 390 for our lens. So there's a pretty big difference there in focal length. And the centers are off by a bit too. So especially the height, the center in the X direction, the ideal where the camera center is, where the image center is 320 pixels, because I have a 640 pixel wide image. So 320 is where the camera center by ideal would be, but as we measure it and estimate it, it's around 345 pixels is the actual value. So you can see they're off by a fair bit, and this all contributes to getting better accurate estimates. And then you see the distortion coefficients. Again, I mentioned I had a positive barrel distortion, radial distortion, which is a barrel type distortion, and the different parameters that get estimated. And you saw in the previous, this is what those parameters do, is they help me correct for those distortions. And then one last thing, as I start to wrap up, is the other thing you get out of this is the ability to compute where this object is relative to the camera, or the vice versa, where the camera is relative to the Chirurco target. So we can do that because we know where all these points are. It gives us an estimate of where the target is. And what I've drawn here is a coordinate axis that is, like I've assumed the origin of the target is in the lower left corner. And so I've mapped that by knowing where the camera is relative to that origin. And so I can do things like understand where that target is relative to the camera in space. And if I had two cameras looking at this target, then I can figure out where each one is relative to the other by mapping them through this shared reference frame, which is the lower left-hand corner of the target. And this is maybe a little bit of a teaser for, this is getting into extrinsic calibration, which I'm not going to talk about. But as you start to do that, you can tie that in with intrinsic calibration to get really good estimates of, for example, where things are on the field, right? If I want to project from the world some point on the field, target in the field into the camera, and then figure out where that is, then I need good intrinsics. If I want to know something about where the cameras are relative to each other, again, I need to unify the information that comes from, say, tracking a ball on the field that might be given from different cameras, then having them have a shared reference point or the extrinsic calibration is going to be really important. And same thing if I want to just map a single camera view into, say, where the robot origin is or the IMU is, I can do that. And there's some really cool stuff that, again, hopefully we'll be able to talk about next year. There's another routine called Caliber that takes IMU data and camera data and fuses them together to figure out where, basically to compute the extrinsic calibration, to figure out where the camera is relative to the IMU and so the robot reference frame. Okay, so with that, I will stop, and I won't take questions right now because this one's going to be offline, but I hope everyone enjoyed that, and definitely if there are questions, happy to answer them offline.